Hello and welcome to Learn 360. In this video, I explain to you the Newton's universal law of gravitation. So it is thought that Sir Isaac Newton was one day in his garden and he was sitting under one of the apple trees in his garden. One of the apples fell down. Interestingly, Sir Isaac Newton started asking himself, why did the apple come down vertically? Not going up or this way or that way, but vertically downwards. Then it means that some way, somehow, something must be pushing it or pulling it towards the earth. At that time, he has invented calculus, so he was trying to understand what is happening using mathematics, where he launched his first textbook, which is called the Principia, and then he explained a lot of things here. So the summary of what he was able to do is now what we are calling the universal law of gravitation. So Sir Newton is saying that two particles of mass m1 and m2 are mutually attracted with equal and opposite forces of magnitude F, given by the product of m1 and m2 and then the inverse square of the distance r between their mass centers. So what we are trying to say is that, mathematically speaking, this force of attraction between the two particles, so J m1 m2 divided by r squared, so proportional to the product, inversely proportional to the square of the distance. This J is what we are calling the universal gravitational constant, given by 6.673 times 10 raised to the power minus 11 meter cube per kilogram second square. Okay, so this is what we are saying. M1 m2 attract each other. Now this force is actually, according to the third law, these forces here are equal in magnitude, opposite in direction, and then collinear. Okay. So a special case of interest to us in mechanics is the attraction force between the earth and a particle near the surface of the earth. So what we are saying is that, let's say I have a particle which is close to the surface of the earth. I want to look at the force of attraction between this particle and the earth. This time around, the distance between the two masses becomes, the mass centers becomes what? The radius of the earth. Now this is actually a particle, and so the radius of the particle is no more really much important. That's why you don't see any r here. So for such case, the attraction force becomes the weight. And so whenever you are near the surface of the earth, just like all of us right here, there is this gravitational pull from the earth, and that is the reason why whenever you throw something up, it comes down. It means that the earth is trying to pull us, and this is what we are calling our weight. And so our weight is nothing but the measure of how the earth is pulling us towards the center of the earth. So we can actually develop an approximate expression for finding the weight W of a particle of mass m. Now, if we assume the earth to be a non-rotating sphere of constant density and having a mass me, then if r is the distance between the earth center and the particle, we have W equals big J m me over r squared. This is the weight, and then this is the mass of the particle, this is the mass of the earth. All right, so if we say let J equals everything here with the exception of the mass, so let J equals everything here with the exception of the small m, then I have what we call weight as mg, and this is a very famous equation which we have been using when we say the weight of a particle or a body is what? Mass times acceleration due to gravity. So this is where it is coming from. Now I have my friend here who is an astronaut. As a matter of fact, once you are in outer space, your gravitational pull reduces, become very, very small. And this is the reason why the astronauts tend to fly. Whenever they are in space, the astronauts tend to fly. You see that they'll be hanging because the gravitational force is very, very small over there. Thank you for watching.